Keeping the lights on across an entire country, it's this huge, complex balancing act. Today, we're going to pull back the curtain on one of the most elegant tools engineers use to manage all that chaos in our power grid. It's a concept called symmetrical components, and trust me, it's way more intuitive than it sounds. Let's get into it.
So pretty much everything, from the giant power plants all the way down to the outlet in your wall, is part of this incredible three-phase system. And in a perfect world, that flow of power is perfectly even, totally stable, and predictable. That balance is the absolute key to having an efficient, reliable grid that keeps everything running smoothly.
But the real world, it's almost never perfect. When things go wrong, they create a problem that engineers just call unbalance.
So what actually happens when that delicate harmony gets shattered? Could be a lightning strike, a downed power line, or even just an uneven load somewhere. Any of those things can throw the whole system into disarray. And this is what you get. Just look at those arrows, the supply voltage vectors. Each one is a phase of power, and you can see they're all different lengths pointing in all sorts of directions. It's just electrical chaos. Trying to analyze this mess directly, it's a total nightmare for an engineer. I mean, how do you fix a problem you can't even properly measure or understand?
Well, way back in 1918, an engineer named Charles LeGeyt Fortescue came up with this just brilliant idea. He figured out a way to see the order hidden inside all that chaos.
And that's the core idea right there. It's almost like a magic trick. Instead of trying to wrestle with one giant, complicated issue, what if you could just break it down into smaller, manageable pieces that you already know how to handle?
And this is a perfect picture of that trick in action. On the left, you've got that chaotic, unbalanced voltage. But by running it through this sort of mathematical prism, you can separate it into three perfectly balanced, symmetrical sets of components. All of a sudden, the chaos starts to make sense.
So here's the crucial takeaway. Symmetrical components is a method that lets engineers take any jumbled, unbalanced system and break it down into three distinct, perfectly balanced systems. And each of those new systems is simple and way, way easier to work with. So, what are these three new systems? Let's meet them. And to make it stick, let's think of them as three different characters, each one with its own personality and its own story to tell about what's happening on the grid. First up, we've got the positive sequence. This is our hero, the workhorse. It represents the ideal, balanced flow of power that we always want. Its three parts are equal in size, they're perfectly spaced 120 degrees apart, and they spin in the right direction. This is the component that's actually doing the useful work, powering our world. Then we have the negative sequence. Think of this one as the saboteur. It's also perfectly balanced, but check this out. It spins in the opposite direction. Its presence is a huge warning sign. It's literally working against the normal flow of power, and it creates stress that can damage big motors and even make the lights in your house flicker. And finally, there's the zero sequence, the disruptor. You can see right away this one's a totally different beast. Here, all three components are equal in size, but they're also perfectly aligned. They're in phase. This one doesn't spin at all, and it only shows up when there's a really serious problem, like a direct fault to the ground. It's a major, major red flag. Okay, so we can break chaos into three neat little packages. It's a cool trick, for sure, but why is it one of the most important tools in power engineering? Let's dig into why this actually matters so much. The engine behind this whole process is, of course, math. A really elegant set of equations lets engineers perform this transformation, letting them peer inside the electrical system with incredible clarity. Now, don't worry, there's not going to be a quiz. But these are the equations that make the magic happen. The ones on the left show how to calculate the simple sequences from the messy, unbalanced values. And the ones on the right show how to put them all back together again. It's a two-way street, which gives engineers complete control over their analysis. But again, why go to all this trouble? Why not just deal with the messy original problem? Why does separating them out matter so much? And here it is. This is the big payoff. It's because each sequence isn't just some abstract math. It corresponds directly to the physical health of the power grid. The positive sequence tells you about normal, healthy operation. The negative sequence is a direct measure of unbalance that's stressing out equipment. And the zero sequence signals a major fault that's causing heat loss and can lead to blackouts. They turn abstract numbers into a real-world diagnosis. So, what this incredible tool gives us is a clear, repeatable process for turning a complex, dangerous problem into a straightforward solution. It's a simple but profoundly powerful workflow. First, you take the chaotic system and you deconstruct it. Then you analyze each of the simple, balanced sequences on its own, which is much, much easier. And finally, you combine those simple solutions to understand and fix the original, complex problem.
And its purpose is crystal clear. As our source material puts it directly, this method is used for fault and system analysis. That's its job. It's how engineers diagnose problems and design the protective systems that keep the grid from failing.
You know, at the end of the day, symmetrical components is more than just a calculation. It's a mindset. It's all about having the right tool to look at a complex mess and find the underlying simplicity. And it's that way of thinking that keeps the lights on for all of us. And that leaves us with a final thought. This was a technique for electrical engineering, sure, but the principle is universal. So what other chaotic, complex problems in our world are just waiting for someone to find the right prism to finally see them clearly?